Greetings everyone! Welcome back to the second day of the 16th International Workshop on Real and Complex Singularities online edition. It's a pleasure to introduce the father-to-be of a baby girl, Raúl Oset-Sinha from Universidade de València. Thank you, Raúl, for kindly accepting our invitation. And please leave your comments and questions using YouTube's comments. Thank you very much.
Okay, thank you, Pedro, for the introduction, and thank you for reminding me that I'm going to be a father again very soon. Hopefully not throughout this talk. So let's see, but it is true that until today I didn't know whether I would be able to give the talk or not. But now here I am, and so thank you for your introduction.
Thank you very much.
Should I start sharing my talk? Oh yeah, there it is. What have I done? Wait, I touched something. Just a second. Okay. So, well, first of all, I would like to thank the organizers for the chance of giving this talk and for having organized this online edition, which is, I imagine, lots of work, but it's working out really, really nicely. And so I thank them for this online edition, but I hope it is the first and the last, because I really prefer the meetings we used to have in São Carlos. Hopefully in 2022 we'll be able to meet in person. And well, my story with the São Carlos workshop dates back to 2006. In 2006 I had I went to the first workshop, and since then I've been to all of them. And that means I've been to 8 out of 16, which is obviously not as much as other people, but it's already a lot. And in fact, I have a very close relationship with this workshop because I have even lived in São Carlos for some time, and I even organized the 14th international workshop. So for all these reasons, it is a pleasure to be here. So well, I'm going to talk about the axial curvature for corank 1 singular surfaces, and this is a joint work with Kentaro Saji. So the scheme of my talk is the following. I will give some background and talk about briefly about some other curvatures. I will talk about the particular case of frontals, and then about the more general case of corank 1 singularities, where I will talk about the umbilic curvature, and finally I will go and talk about the axial curvature. Okay, so first of all, frontals. Frontals are some very natural objects to study in geometry because they appear naturally. They appear naturally as parallel surfaces of immersed surfaces, regular surfaces, or as developable surfaces of space curves. Also in contact geometry, frontals appear. In physics, in several areas of physics like optics or cosmology, and even in dynamical systems. The thing is that for frontals, there is a geometrical structure which allows one to develop differential geometry and to study geometric invariants. But how about any corank 1 singular surface? For frontals, I will explain in a moment which is this geometrical structure. But if you consider any corank 1 singular surface, how can you define a certain curvature which gives some geometrical interpretation? So that's what I'm going to explain today. Just to put into context of this subject, in the last 10 years, there have been more than 70 papers in differential geometry, out of which 90% are about frontals. And of that 10% which are not about frontals, there are probably only 1 or 2 which are not about the crosscut, which means that most of the ones that are not about frontals are just about the crosscut. It is difficult to study differential geometry of singularities in general. So, well, what is a frontal? A frontal is just a map germ that has a well-defined normal at each point, okay? So we have this unit normal vector field, which means that if you take the differential of any tangent vector at P, this product has to be 0 with this normal for any P in a neighborhood of the origin. In the special case where the pair F and the normal is an immersion, well, I put here a Legendre immersion because this is the projective eyes of the cotangent bundle. But in the case that this is an immersion, then we have a wavefront. And in the case it is not an immersion, it is just a frontal. So here we have some examples, the cuspidal edge and the swallowtail, which are these two pictures over here, and the cuspidal crosscut. The cuspidal crosscut is an example of a frontal which is not a wavefront. And these three, by the way, are the only generic frontal singularities of surfaces. So if we consider the signed area density function, which is this lambda here, the singular set of the map F can be seen as the preimage of 0 by this lambda. And we call a singular point non-degenerate if the differential of this lambda is non-zero. And at a non-degenerate singular point, there is a vector field such that the differential of F acting over this vector field is 0 on the singular set. This is called a null vector field. A singular point is called the first kind if this null vector field acting over lambda is different to 0. And if we have a singular point of the first kind, then this null vector field is transversal to the singular set. So we can consider another vector field, xi, which is tangent. And in that way, we have that psi eta is positively oriented. And finally, if gamma is the parameterization of the singular curve, because when we have a non-degenerate singular point, the singular set is a curve. So if gamma is the parameterization of the singular curve, we call gamma hat the image of this. So for first kind singularities, we can define, for example, the singular curvature, the limiting normal curvature, the cuspidal curvature, and the cusp directional torsion. The formulas for these are the following. For example, the singular curvature can be defined in this way, where gamma hat, remember, is the image of the singular curve, and nu is the normal. This formula might remind you of the geodesic curvature, actually. And in fact, the singular curvature is the limiting geodesic curvature when you get to the singular curve. Okay. Then you have the limiting normal curvature, which, as the name indicates, is also a limit of normal curvatures when you get to the singular curve. And using the vector fields we defined before, you have these terrible formulas which define the cuspidal curvature and the cusp directional torsion. As you can see, the structure of the normal and the structure of the null vector field and this other psi vector field enables us to define relatively easily certain curvatures. Obviously, these formulas don't mean much, but if we go to these pictures, maybe you can get a better idea of what these curvatures mean. For example, the singular curvature is the geodesic curvature of this cuspidal edge here. Here, the limiting normal curvature, you see the well-defined normal is this over here. And so the limiting normal curvature is the curvature of the cuspidal edge with respect to the normal. The cusp directional torsion is how the surface rotates along the cuspidal edge, more or less. And the cuspidal curvature tells you about the openness of the cuspidal edge. Okay. So, well, there are many there's lots of geometrical information you can get from this curvature. In fact, in January, I gave a talk in IMPA where I did a small survey of this kind of curvatures, of results involving this kind of curvatures. But today I will only mention results with mainly with the singular curvature, which is the one I'm more interested in, because it's related to the axial curvature I will talk about later. So, well, first of all, for cuspidal edges, Martins and Sagi, they managed to prove that if kappa is the curvature of the cuspidal edge as a space curve, then kappa squared is equal to the singular curvature squared plus the normal curvature squared. And this also might remind you from the regular case. In the regular case, you have here this formula with the geodesic curvature and with the normal curvature. And more importantly, if you consider two map germs, they proved also in that same paper that if you consider two map germs that are cuspidal edges at 0, and if they share the same 6 invariants, we have the 4 defined plus the derivatives of 2 of them, then there exists a diffeomorphism in the source and an isometry in the target such that they are equal up to third degree. Okay, this means that these curvatures determine cuspidal edges geometrically up to order 3. So they are important in that sense. But let's go to some important results regarding these curvatures. For example, in their paper in Annals, Saji, Umehara, and Yamada, they prove the following. If you have a front is a wavefront, okay? And you consider K the Gaussian curvature, which is defined on the set of regular points, then K dA prime, which is defined as K times the signed area density function du dv. This can be extended continuously as a 2-form on the whole surface, okay, even on the singular set. This is interesting because the Gaussian curvature obviously can tend to infinity when you tend to the singular set, but in any case, for wavefronts, this is a well-defined 2-form globally. Okay. So with this, they managed to prove a Gauss-Bonnet formula for certain wavefronts. In the case that we have an oriented compact to manifold, and F is a wavefront, which admits at most peak singularities. Peak singularities are basically singularities that have curves of cuspidal edges going towards them. For example, a swallowtail, or the birth of 2 swallowtails would have 4 cuspidal edges going towards it. So those are peak singularities. So when you have a front with this kind of singularities, then you have that the integral of this well-defined 2-form plus 2 times the integral on the singular set of the singular curvature is equal to 2 pi times the Euler characteristic. Okay, so it is very interesting to recover the Gauss-Bonnet formula, but you have to introduce the singular curvature over the singular set. There is another result and that is interesting, and this is the Klingenberg-type formula. So imagine you have a regular surface in R3, and you have an orthogonal projection to a plane P. Okay. Then Klingenberg proved that the Gaussian curvature is equal to the product of the curvature of the normal section times the curvature of the apparent contour. That is, I don't know if you can see this correctly. I have the YouTube window open, but it has some delay, so I don't know if you can see this properly. But basically, you have the surface, you're projecting it to a certain plane, and the apparent contour is the image of the singular set. And this has a certain curvature, and the normal sector has a different curvature. The product of these curvatures is equal to the Gaussian curvature. This is interesting because, for example, it means that if in the apparent contour you have an inflection point, that means that it can only come from a surface, from a projection from a surface from a parabolic point. Okay, so there is some geometrical interesting information you can get from there. But well, Sagi proved that the cuspidal for a cuspidal edge, you can prove a kind of Klingenberg-type formula. The idea is if you consider xi as the cross product of the normal times the tangent to the cuspidal edge, then let's try it over here now. So you have the cuspidal edge, you have this well-defined normal, you have the tangent to the cuspidal edge, and you have psi, okay? And you consider the normal plane. You consider v theta as a vector in that normal plane, and you consider the orthogonal projection. Then you obtain that this well-defined two form again is equal to this over here. And here you again obtain you have the curvature of the projection, you have the curvature of the intersection with that normal plane, and you have the singular curvature. So you can recover a corank type formula, but again, the singular curvature appears. Okay, so this is some results I wanted to talk about frontals and curvatures that have been defined before. But now let's forget frontals and go to a more general setting, which is any corank one singularity of a surface. Okay, so for this setting, I consider M my corank one singular surface. That means it has a corank one singularity of the parametrization at P. And I'm going to consider this seen as the image of a corank one map from a regular surface M tilde to R3. Okay, and phi is just the local coordinate system of my regular surface. So here is G, here is phi. F is the composition of G with phi minus 1. Okay, so F is the parametrization of my singular manifold and goes from R2 to A. Okay. Okay, so with this setting, I can define a first fundamental form. But in order to define the first fundamental form, instead of defining it over the tangent space at P to M, I'm going to, because this tangent space at M is just a line, because it has corank 1, I'm going to define it in the tangent space, in the product of tangent spaces of the regular surface. Okay, and I define the first fundamental form of xy as the differential of g over x times the differential of g over y. Obviously, this is not a metric. This is a pseudometric. Why? Because you can have g has corank 1, so you can have a non-zero vector here, and this could be 0. Okay. Okay, but at least I have a first fundamental form, and I can also define a second fundamental form, which is just taking I define it over the basis of this tangent space, and this is just the projection on the normal space of this second derivative. So I define it on the basis, and then I can extend it to the whole space in a unique way as a symmetric bilinear map. So I have a first and second fundamental form. Great. Then I can do the following. Martins and Nuño Ballestero, following the idea of the curvature ellipse that was defined for surfaces in R4, regular surfaces in R4, we can define a curvature parabola for singular surfaces. How? We consider the subset of unit tangent vectors in the tangent space. We call it CQ, and we consider the map that goes from CQ to the normal space given by eta of x is the second fundamental form of XX. So the curvature parabola is the image of CQ. So it is the image by the second fundamental form of the unitary vectors. Okay. Here you have a picture. Imagine you have your singular surface. Here it is a crosscut. And here we have the tangent space to M tilde. The unitary tangent vectors are not an S1 because we don't have a metric. We have a pseudometric. The unitary tangent vectors are two straight lines. And the image by the second fundamental form to the normal plane is a parabola, which is this parabola over here. Okay, so first of all, something related to the parabola is that the parabola can be degenerate. It is non-degenerate when we have a cross-curve, but otherwise it will be degenerate, and it can be either a half line if the two jet is equivalent to this. That means these are the fold singularities, which Mont called fold singularities. It is a line if the two jet is this. For example, the swallowtail is in here, and it is a point if the two jet is this of the parametrization. Okay, so with this curvature parabola, now we can define a curvature, and that's what Martins and Nuño Ballesteros did. In the case that the curvature parabola is degenerate, that is a half line or a point, given an adaptive frame, which I'll explain later on, don't worry about this, but they defined the umbilic curvature as the component on this vector of the second fundamental form. Here you have a picture. So imagine this is your adapted frame. Don't worry about these infinities here, but just consider this frame. And if you notice here, this component does not depend on x. So this kappa u does not depend on x and is well defined. And it is basically projecting to this vector and taking this value over here. In the case that it is a point, the distance from P to the point, to the curvature parabola, is the umbilic curvature. So what did they manage to, what geometrical information could they obtain from this umbilic curvature? First of all, contact with planes. They studied height functions, and they proved that a height function in a direction V has a singularity of corank 2, which means that the contact with the plane orthogonal to V has corank 2 contact. And it has corank 2 if and only if the parabola is degenerate and the umbilic curvature is 0, and V is an infinite binormal direction, which again I will define later. But more interestingly is that if you consider distance squared functions, that is contact with spheres, then the distance squared function has a singularity of corank 2 if and only if the parabola is degenerate, kappa u is non-zero, and u is exactly this. So this is why it's called umbilic curvature, because it tells you the distance to the umbilical focus. In the focal set, that is the centers of spheres with degenerate contact, you have a unique, in this case, you have a unique umbilical focus, which is the center of a sphere with corank 2 contact with the surface. And more interestingly, they also managed to prove, Martins and Sati proved, that in the case of frontals, in the case of cuspidal edge, sorry, if nu is the unit normal vector field, then nu is orthogonal to the line that contains the curvature parabola, which is degenerate in this case. And the umbilic curvature is equal to the absolute value of the limiting normal curvature. This is very interesting because, for example, Teramoto proved that for certain frontals or wavefronts, the limiting normal curvature is a kind of principal curvature for wavefront singularities. So this means that in a sense, the umbilic curvature is a kind of principal curvature for singular corank 1 surfaces. And if you think about it, you are projecting the curvature parabola and you have a similar idea for the curvature ellipse, but I won't go into that. So that's... Okay, in fact, this umbilic curvature is also interesting because it can be defined in many other contexts. With my former student, Pedro, who introduced me before, and Sidinya, we defined an umbilic curvature for singular corank 1 surfaces in R4. But here, the normal space is not a plane. The normal space is a 3 space. So we managed to define the umbilic curvature even for the case of a non-degenerate parabola. And basically, if you consider the affine P to be the minimum affine subspace which contains the curvature parabola, so this plane, the umbilic curvature is the distance from P to this plane, for example. And this umbilical curvature, and here again, it measures in another paper with Jorge Dolindo, we've proved that this umbilic curvature also gives you the distance to the unique umbilical focus in the focal set. But anyways, going back to our subject, let's start with the axial curvature. So we can define an axial vector, okay? Consider the curvature parabola to be, in this case, a non-degenerate parabola. When you have a non-degenerate parabola, there's always a symmetry axis and a directrix, okay? So we are going to call the axial vector to the unit vector that is parallel to this direction, to the symmetry axis. And we are going to consider an adapted frame where VA and VD is parallel to the directrix. So VA, VD is a positive oriented orthonormal basis. In the case that delta, the curvature parabola, is a line or a half line, we take the axial vector as the direction of the line. Okay? And when the curvature parabola is a point, which is not the origin, then we take the axial vector such that it is orthogonal to the direction of the point. Okay, and this is an orthonormal oriented basis. Okay, so this is the frame I'm considering. And now, with a frame like this, where with the axial vector, we can define the axial normal curvature function, which is just the scalar product of the second fundamental form acting on xx times this axial vector. Here, this does depend on x, because this, well, I'll just explain that. But if you consider x a unitary tangent vector, then remember the unitary tangent vectors were two lines here. So I can write x in this way. So I can consider the parameter y to describe x. And I define the axial curvature as the minimum of the axial normal curvature function. Or, in other words, the minimum of eta of y, where eta is this, times VA. Okay, so this minimum is not always defined, obviously, but when it exists, this is the axial curvature. What is the geometrical interpretation? Well, the geometrical interpretation is something like this. So if we have our parabola here, and this is the axial vector, we project the parabola on this direction, and this value over here is the axial curvature. Okay, it is the projection on the axial. And here, when you have the parabola is a half line, you can project it to, again, in this direction, and this is the axial. Here also, this gives you the umbilical curvature. Okay, so when it is a line, the projection, exactly, when the curvature parabola is a whole line, and you project it on that direction, you get the whole line again, so there is no minimum. In this case, the axial curvature is not bounded. And when it is a point, the projection is the origin, and the axial curvature is 0. Here you have some pictures of when the axial curvature is 0. For example, you have a parabola such that this extremal point is in parallel to this direction, then the projection to VA will be 0. Or you have a half line. Here again, the projection to VA is 0. Or you have a half line that starts at the origin, also 0, or it is a point. In these cases, the axial curvature is 0. Good. So let's study some properties about the axial curvature and what geometrical information we can obtain. First of all, if you have a surface given in Mont form, that means since it is corank 1, we can have the only linear term to be u, and then no linear terms in these two components and the 2jet, we can write it like this. So for a a surface written in this way, the axial curvature can be obtained by this formula. This is great because it is very easy to calculate. But of course, you don't always have a surface given in Monge form. So it would be interesting to obtain a formula even when you don't have a Monge form. And for that, we obtain the following. So in the case that the axial curvature is a non-degenerate parabola or a half-line, this means that it is a cross-cap or a fold type singularity. Otherwise, it is infinity or zero. So if we suppose that the derivative with respect to u is non-zero, the derivative with respect to v is zero, and these three other conditions, then we have this nice tidy formula for the axial curvature. But we want a kind of coordinate independent formula, and this is still asking too much for the parametrization. So if we have something more general, not so tidy, but much more general. That is, if the coordinate system satisfies that the partial with respect to u is non-zero and the partial with respect to v is zero, this is very trivial because we are in corank 1. So you can always have something like this. This is quite common, okay? Not so, you are not asking too much to the parametrization. And in this case, the axial curvature has this formula. So again, it is easy to calculate. And there is something even more interesting about this axial curvature, and this is the following. The axial curvature can be given in terms of the coefficients of the first fundamental form. And this means that the axial curvature is an intrinsic invariant. This is surprising because it is defined using a normal. It is defined using the curvature parabola in the normal plane. And so the fact of this axial curvature being an intrinsic invariant is interesting, and we will see later on why it is interesting. So first of all, there is something we have to say about this axial curvature. This axial curvature is related to the singular curvature I was talking about before in the case of frontals. In what way? So we have imagine you have a map germ where Q is a non-degenerate frontal singularity, and nu is the unit normal vector field that we have along frontal type singularities. Then we have the following, that this nu is orthogonal to the axial vector. Okay, the normal of the frontal is orthogonal to the axial vector, and that the axial curvature is zero if and only if the curvature parabola is a point, or the second fundamental form is parallel to the normal of the frontal, where x is a non-zero tangent vector of the singular set. And finally, the axial curvature in absolute value is equal to the singular curvature in absolute value. This means that, ignoring the sign, the axial curvature is a generalization of the singular curvature for non-frontal singularities. Okay? And this is where it gets very interesting, because remember that the Gauss-Bonnet formula had been proved with the singular curvature for certain frontal singularities. There was also this Klingenberg-type formula, and there are many results in wavefronts and frontals using this singular curvature. So now the axial curvature is a generalization, and we can expect to generalize all these results to other corank 1 singularities. So as corollaries of this, we can extend and recover and extend many results about the singular curvature. For example, in the paper in Annals, Saji, Umehara, and Yamada proved that the singular curvature was an intrinsic invariant for the cuspidal edge. With this, we have proven that since we proved that it was intrinsic, the axial curvature, then this means that the singular curvature is intrinsic for many different frontal singularities. It also talks about the unboundedness of the singular curvature. For example, in that same paper, they proved that the singular curvature tends to infinity when you tend to a swallowtail point through the cuspidal edge. And this is explained by our axial curvature, because the swallowtail, the curvature parabola at the swallowtail point is a whole line, and so the axial curvature is not bounded. So there again, you have certain explanations. Good. So now let's go to some geometry we can get from this axial curvature. And first of all, let's consider contact with planes. So again, when the curvature parabola is non-degenerate or a half-line, the singularities of the height function on the axial vector direction are a1 plus if and only if the axial curvature is positive, and a1 minus if and only if the axial the axial curvature is negative. What does this mean? This means that if the axial curvature is negative, then you don't have a plane such that the surface is only on one side of the plane. Okay. In other words, if the axial curvature is positive, then you have a plane which is orthogonal to the axial vector, such that the surface lies only on one side of this plane. And the singularity of the height function is worse than a1 if and only if the axial curvature is 0. In particular, you have this. So here you have an example of a cuspidal edge with positive axial curvature, and here you have a plane that leaves the surface on one side. And here you have a cuspidal edge with negative axial curvature, and you don't have this plane. Okay. Good. Now let me define asymptotic directions and binormal directions. So if you have a non-zero tangent direction, it is called asymptotic if there exists a normal vector such that the second fundamental form of uv times the normal is 0 for all v tangent. Okay. So this is the definition of asymptotic, and in this case, this nu here is what we call a binormal direction. It's a kind of extension of the definition you have of asymptotic direction for the regular case. Here you have some pictures of the curvature parabola, and it turns out that for asymptotic directions, the image of the asymptotic direction by the second fundamental form is tangent to the curvature parabola. So for example, here you have two asymptotic directions. Here you have 1, here you have 0. And here, in the case of a degenerate parabola, you can have also 2 or infinite asymptotic directions. This y infinity is a kind of asymptotic infinite direction which corresponds to delta v in the tangent space. I'm not going to explain this, but if you are interested in understanding what an infinite asymptotic direction at a singular point means, there is a paper by Pedro Benedini, Raúl, and myself where we explain the nature of these infinite asymptotic directions. Okay, but so the thing is that in the case that the axial curvature is defined, the axial curvature is 0 if and only if the axial vector is a binormal direction. So it also tells you something about this normal direction. And in fact, similarly to the regular case, this in the regular case is obvious, but we have a corollary that is that if the height function has a degenerate singularity, if and only if V is a binormal direction, this is what is trivial in the regular case, not so here. And the singularity is of corank 2 if and only if the curvature parabola is degenerate and both the axial and the umbilic curvature are 0. Okay. Good. So now let's study a little bit further this axial curvature. First of all, a singular corank 1 point is called elliptic, hyperbolic, parabolic, or an inflection point if and only if it has 0, 2, 1, or infinite asymptotic directions. This is similar to the regular case again. But there is a problem. Here I have a picture of an elliptic crosscut, okay? And here I have a picture of a hyperbolic crosscut. But both have negative axial curvature. And this means that there isn't a plane such that the surface lies only on one side of this plane. And this is not what happens in the regular case. If you remember, in the regular case, an elliptic point, there is a plane such that the surface is only on one side. And at a hyperbolic point, there isn't. But for singular points, you can have elliptic and hyperbolic points that don't have this plane. And what defines if there is this plane or not is the axial curvature. So given, for example, a crosscut with negative axial curvature, how can I distinguish when it is an elliptic crosscut or a hyperbolic crosscut? Well, we found this interesting result, which says the following. If we have a non-degenerate parabola, which means that it is a crosscut, suppose that we have negative axial curvature, then P is elliptic if and only if the intersection of the surface with the plane orthogonal to the axial vector is two tangent quadratic curves which lie in the same half plane, and hyperbolic if they lie in different half planes. Here you have the picture. Okay. Here, this is the left-hand side crosscut from before. It was elliptic, and we have two tangent quadratic curves which lie on the same half plane. And this is the hyperbolic crosscut we have, and we have two tangent quadratic curves which intersect in different half planes, which are in different half planes. And also for parabolic crosscuts, this happens if and only if one of the curves is a straight line. Also for cuspidal edges, we can distinguish when it is a hyperbolic cuspidal edge or an inflection cuspidal edge. There are no elliptic cuspidal edges, okay? This is because, well, there are many reasons for this, but cuspidal edge can only be either a hyperbolic point or an inflection point. So when we have negative axial curvature, P is a hyperbolic point if and only if the intersection of the surface with the plane orthogonal to the axial vector is two tangent cubic curves which meet at two local maxima or two local minima. And it is an inflection if at least one of the curves has an inflection point at the origin. So here you have two examples of, here you have the cuspidal edge with a hyperbolic point and the intersection. Here you have a cubic curve over here and another cubic curve over here, which are tangent at two local minima. And here, for the inflection point of this cuspidal edge, we have an inflection point for this curve and, in fact, another inflection point for this curve. Actually, we tried to do a general result for any kind of singularity, not only crosscuts and cuspidal edges. And in fact, for hyperbolic points, we have a global criteria for any singularity. But for inflection points, it depends on the type of singularity. So we decided not to write a general statement. Anyways, let's go on to something different. And to finish, I want to talk about how to relate the Gaussian curvature with the axial curvature. Okay? I'm going to talk about only fold singularities because for the crosscut, for example, the Gauss-Bonnet has been proved, and also Klingenberg-type formulas have been proved, but not for fold-type singularities. So if you have a fold-type singularity, we can write f in this way, where obviously a2 of 0, 0 has to be 1, so that we have this b squared, and some functions over here. Okay, the interesting thing is that if B1 of 0 is non-zero, that is, if we have the term U squared B, this includes S1 or BK singularities in Mond's list, we can define the following map from R times S1 to R2. And this is a kind of blow-up because in a singular corank one point of this type, there is not a well-defined normal like you have for frontals. So how do you define the Gaussian curvature? What we are going to do is a kind of blow-up in order to be able to define, to have a well-defined normal. Using this map, if I consider the pullback of the cross product of FU times FB and I divide by R squared cosine theta, and I normalize this, then I have a well-defined normal, an analytic function, okay? An analytic map, sorry, defined on R times S1. If instead of B1 equals 0, you want one of these conditions, then you take this different blow-up. And with this coordinate system, the Gaussian curvature can be expressed in this way. So we have the following result, that for fold singularities with B1 of 0 different to 0, the boundedness of the Gaussian curvature depends on this term over here. And this term over here, you can see that the axial curvature appears and the umbilical curvature appears. Okay, so we have related the Gaussian curvature of the blow-up with the axial curvature and the umbilic curvature. What we were trying is to obtain a coenzyme type formula like the one I showed before, but we found a problem. The problem is that if you consider xi a normal vector and let kappa 1 be the curvature of the apparent contour of the projection along psi, then this term, which controls the boundedness of the Gaussian curvature, can be expressed in this way. So we have the axial curvature, we have the curvature of the apparent contour, but we have this term over here. And we were unable to express this term as the curvature of a normal section. So in this sense, this is not a coenzyme type formula for any corank one singularity. But we obtained a byproduct, which is the following. This term over here is interesting in itself because if it is non-zero, this implies that F is not a frontal. So this term is an obstruction to frontality. Okay, if it is not 0, you have a corank one singular point which is not a frontal. Good. So this is what we have proved up to now. Future work is, as I said, we would like to be able to prove a Gauss-Bonnet theorem for any corank one singularity using the axial curvature. Remember that for the certain frontal type singularities, this was proved with the singular curvature, and this is a generalization of the singular curvature. My intuition tells me that if you have an isolated corank one singularity, like a cross-cap, for example, the Gauss-Bonnet formula will be the same as in the regular case. So the axial curvature will not appear in the formula, although it might be necessary in the proof. Another thing we would like to understand is the meaning of the sum of the squares of the umbilic curvature plus the axial curvature squared for this kind of singularities. I know it is the curvature of a certain curve, but what is the meaning of this curve in these singular surfaces? For frontals, obviously, it is the cuspidal edge, but for any other corank one singularity, we don't know. And also, remember, we managed to define all these curvatures because we were in corank 1 and we had a first fundamental form. But if you are not in corank 1, if you're in corank 2 singularity, how can you define a geometric invariant? How can you define a certain curvature which gives you geometrical information about the surface? I don't know. This is future work. So, well, thank you all for listening. Thank you for your attention. And happy birthday, Sao Carlos. I hope this workshop lasts for another 30 years and I can go to all these marvelous workshops.
Thank you, Raúl, for the excellent talk. Let's wait and see for some comments and questions. Please leave your comment and question using this chat on YouTube, and we'll be asking directly to Raúl. I have a question. Is it natural to extend this new curvature to corank one surfaces in higher dimensions, right?
Yes.
4 or 5 in higher dimensions.
Surfaces in higher dimensions, you still have the curvature parabola, but this curvature parabola will always be in a plane, but it can be in a plane which does not go through the origin of the normal space. So you can still consider the projection in a certain direction, but it has to be the projection inside this plane. If the curvature parabola is degenerate, then the affine space does pass through the point P, so you define it in the same way. When it is up here, you have to consider not the projection to the axial curvatures, but over here. Okay. I see a question from Matthias. Are the curvatures you are considering related to the Lipschitz-Killing curvatures? I think there already exist Gauss-Bonnet theorems for singularities in that context. Well, Matthias, I am not sure if they are related, and I am not aware of the papers you are talking about. Later on, please send me the references to these papers. I know that Gauss-Bonnet has been proved for surfaces with only cross-cap singularities, for example. This has been proved recently, but it had also been noticed by Werner Boy 100 years ago. But I am not sure for different kind of singularities.
Let's see, let's wait. Oh, I have another question, Weil. You said we can define, but can we expect the same times of results? Meaning this curvature will be an intrinsic invariant for those type of surfaces or not? Not sure.
I don't know. I think it could be possible, yes. Probably is. In fact, I remember a talk by Ishikawa in the workshop in Valencia in last October, where he was defining some certain frontals in R4. I think that maybe this axial curvature could be a kind of singular curvature for those type of frontals. I'm not sure. I have to think about this. I mean, there are still many things that can be thought of with respect to this axial curvature.
We'll find out. And Georgie asked if this B1 can be some invariant.
That's the point. We didn't manage to find any. Well, it is an invariant, but we couldn't express it as a curvature of a normal section, which is what we wanted for a coordinating type formula. What kind of invariant it is, I'm not sure, but for sure there is some certain curvature which detects this, and it would be very interesting because it's an obstruction to frontality, so it would be an interesting curvature.
Another question from Yang-Ling Li. What frontally means? It means frontals?
Sorry, well, what frontality? Yeah, an obstruction to frontality. When I say this, I mean that if this is non-zero, then it is not a frontal. It's an obstruction to being a frontal.
Let's see. I guess this is it. Well, once again, thank you very much, Raúl, for the talk. And we were looking for the new baby singularist.
I can tell you that my baby hasn't been born yet. Luckily. Okay, it's been a pleasure. I'll see you in the coffee break.
See ya. Thank you very much. I have a message. Yesterday's videos will be available soon in our YouTube channel very soon. Thank you. Oh, there's another question. There's another question.
There's another question. Oh, this question, this is a difficult question. Rémi Langevin is asking if cohendering results were already stated by Durkheim at the end of the 19th century. I have absolutely no idea. These results, when cohendering proved them, I think it was in the 70s. And in the book by, I think it is Bruce and Gibson, or Giblin and Bruce, I'm not sure. They found these results and they started talking about them, but nobody, when what I've read, nobody mentioned any references to before that. In fact, it was surprising that such an easy formula hadn't been proved before. So if it may be possible that it was proved in the 19th century. Yeah.
Okay, thank you very much. And we'll be back at 10 past 10.
Hello, everyone. We are back for the second talk of today. Many thanks, Raúl, for the brilliant talk about fronts, which is a rich field of applications, including dynamical systems. And dynamical systems is the subject of the next talk. So we now fly from Spain directly to Portugal to receive Alexandre Rodrigues. Alexandre Rodrigues is from University of Porto, Portugal, and he will speak about unfolding a Bykov attractor from an attracting torus to strange attractors. Thank you very much, Alexandre, for being with us. And please, now it's your time. Thank you.
Okay. So, first of all, thank you for the invitation. It's a great pleasure to be here, working in your workshop. In this talk is more or less a talk of. So I'm going to be the full screen. Are you observing the full screen? It's okay. Okay.
Yes, that's perfect.
Okay. So
just a second. It's yeah. Okay. Now we can open. Oops. It's black yet?
It's black?
It is black yet.
Wait, let me.
We were seeing.
Let me try again. Once
yeah. It's okay now.
It's okay?
Black now. Maybe you were trying to put in full screen, yeah?
Yes.
When you, now I can see perfectly.
So in full screen you can see, you can observe.
That's right. Maybe that's because you shared.
Okay. So I'm going to share this document like it is. Okay.
Yeah, I think the font is good, so we can see
okay.
we can see this the presentation. All right. Okay.
Okay. So I'm going to use this type of slide. Okay. So during this talk, I'm going to speak about unfolding a Bykov attractor from an attracting torus to strange attractors. There are several words here that seem very strange. Bykov attractor, strange attractors. So let's define some terms before going into details. So this work is a part of work that has been already published in Journal of Dynamics and Differential Equations. And this is a part of another work. I'm going to present another work with Luís Castro. This talk is divided in 5 parts. First of all, I'm going to define chaos, strange attractors. Secondly, I'm going to connect singularities and heteroclinic cycles. In the third part, I'm going to define a Bykov attractor. And in the fourth part, I'm going to analyze the numerical examples. And finally, I'm going to present some conclusions. During this talk, I'm going to avoid technicalities. So all details will be omitted. This is a conceptual work. This means that I would like to point out in which situations I can have strange attractors from a singularity. So it's a conceptual work. So this talk is divided in 5 parts. So if you miss part n, you can find yourself in part n+1. So I think that since it's a very geometrical talk, I think that you can find yourself if you get lost and understand the talk. So the main goal of my talk is to study the role of singularities to generate strange attractors. But what is a strange attractor? A strange attractor basically is connected with chaos. But what is chaos? Okay, so in the first part, I'm going to define Gauss and strange attractors, define examples and some difficulties. Okay, so first of all, let's define Gauss. Suppose that XD is a metric space, so X is a non-empty set, D is a metric, and F is a map. And pair of F is the set of all periodic points of F. Okay? We say that the map F is chaotic if the closure, the topological closure of the periodic points is X. What does it mean? It means that a point in X is either periodic or is very close to a periodic point. Okay? Another property is that F has sensitive dependence on initial conditions. This means that if you start with two different initial conditions, after some time, if you wait some time, the forward orbits will diverge. Okay, the distance between the forward orbit is greater than a given number. Okay, and F has a dense orbit. The idea that you should have in mind is that the orbit will visit all open sets in X. Okay, so this is definition of Gauss. Okay, the first example is a paradigmatic example. It's called the quadratic family. Okay, so suppose that X is the interval 0, 1, and the map is this one. The map F is this one when mu is a parameter that is greater than 5, for example. Okay, the graph of F is this red curve. Okay, so in terms of fixed points, you have 0 and you have another fixed point here. If I consider lambda as the set of points in the interval 0, 1 such that the iterates of its iterates under F is contained in 0, 1, okay, this gives rise to infinitely many points that are in these small intervals, okay? And this map is chaotic, okay? It's chaotic, and lambda is, once again, these points that are here, okay? Infinitely many points, okay? This is the first example of chaotic map, okay? It's the paradigmatic example in dimensional 1, okay? There are several examples, of course. The other paradigmatic example in dimension 2 is the small horseshoe. And for those that are not familiar with this small horseshoe, I'm going to describe the example briefly. So suppose that we are in R2 and we have a square, the square of size 1, okay? Each side measures 1. Suppose that in the horizontal direction, you contract 3 times, for example, 3 times. So this becomes a rectangle like this. And in the vertical direction, you expand 3 times. So this gives rise to a rectangle like this. Then fold this strip and put inside the initial square. Sorry. And put inside the put inside the initial square. Okay? This is the horseshoe map because, this is the horseshoe map because it has the shape of an horseshoe. Okay? And suppose that I'm going to apply this map infinitely many times. This map has inverse. Okay, so it's possible to, the inverse is the expansion in the horizontal direction and contraction in the vertical direction. Okay, so if I define lambda as the set of the points in the square such that its iterates under F is, lies inside the initial square, F restricted to gamma is a chaotic map. Is a theorem, but I think that you may believe me that is in fact a chaotic map. And the set of points are inside the intersection of these, inside the intersection of these rectangles, the yellow rectangles and the green rectangles. So the lambda is inside is the point that corresponds to infinitely many intersections of these rectangles. Okay, so this map is chaotic, and the proof, the classical proof to show that the map is chaotic is to use a shift. Okay, so sometimes we say that F is topological conjugate to a Bernoulli shift onto symbols. So to prove the existence of chaos, sometimes you construct a conjugacy between this set and the shift, the bilateral shift. Okay, okay. So I presented you two examples of chaotic systems. The problem is that almost all points in both examples, almost all points go away after some time. Okay, so in terms of dynamical systems, this is the classical definition of chaos. But in terms of physics, the sets that exhibit chaos are not observable. So we need another definition, a better definition. Okay, so the next definition is definition of strange attractor. The idea is, suppose that F is a diffeomorphism defined in the compact and in Rn. Suppose that it is defined in Rn. A strange attractor for the diffeomorphism is a compact invariant set such that there exists a dense orbit, so is more or less the definition of Devaney that I presented 3 slides ago, with a positive Lyapunov exponent. What does it mean? Basically, a positive Lyapunov exponent is that you have exponential growth of the derivative. So you expand. There exists a direction in which you expand. Moreover, the basin of attraction of gamma, that is the set of points that are attracted to gamma, contains an open set. Since it contains an open set, it has positive Lebesgue measure. So, in terms of physics, this definition of chaos is better because it contains, the basin of attraction contains an open set. This means that there exists, is observable, okay? And a vector field, if I work with vector field, a vector field possesses a strange attractor if the first return map to a given cross-section as a strange attractor. Okay? Okay, so paradigmatic examples of strange attractors. Of course, you have heard about these examples. This is the classical Lorentz flow, okay, is a strange attractor. There are some authors that call is robustly transitive. Okay, if you perturb a little bit vector field, you still have a strange attractor, and the Enon map for maps. Okay, so the Enon map is not robustly transitive, but is another example of strange attractor. Okay, okay. So, but in general, it is very difficult to find strange attractors. To find examples, explicit examples of strange attractors, in general, is very difficult. We have the Enon, we have the Lorentz, and almost all strange attractors have the same properties of the Lorentz or the Enon. Okay, and there are mechanisms to obtain strange attractors. The first mechanism to obtain strange attractors is through the homoclinic tangencies associated to a dissipative periodic point. So suppose that F mu is a family of diffeomorphisms such that P is a periodic point, a fixed point. Okay? Suppose that this associated to this fixed point, I have the stable manifold. The stable manifold basically is the set of points that converge to P, and the unstable manifold, okay, is the set of points that converge to P in negative time, okay. And suppose that I have here for mu equal to 0 a tangency. There are results saying that in this family, there are strange attractors when I pass through no intersection, tangency to transversality. In this transition, there are strange attractors. So if I find diffeomorphism such that I can exhibit homoclinic tangency, is a mechanism to obtain strange attractor. Okay, but once again, is a difficult problem. So could you describe a systematic way to obtain homoclinic tangencies? Is the problem, because if I have homoclinic tangencies, I have strange attractors. And in this talk, I'm going to deal with singularities. How singularities can help us to obtain strange attractors. And finally, I'm going to exhibit a system with symmetry, okay, in which I can find strange attractors. Okay, so summing up, in the first part, I presented definition of chaos, the classical definition of chaos, okay? Problem of the classical definition of chaos. In general, the chaos may not be observable, okay? The set of chaos the set of points that exhibit chaos can have a zero-bag measure. Other definition, strange attractor. The definition is good because I can find it allows observable chaos, but it's very difficult to exhibit examples with strange attractors. Okay, part one is okay? Miriam, part one is okay?
Yes, that's perfect.
Okay, let's go now to part two. If I go, okay. So now I'm going to describe a singularity. I'm going to describe some details about a given singularity. It's called the op-zero singularity. And I'm going to describe how I can obtain a heteroclinic cycle from op-zero singularity. But you can ask, but this is nothing to do with the first part. Wait a moment, okay? So what is the op-zero singularity? Basically, suppose that I have a vector field in R3. And suppose that the origin is an equilibrium of the vector field. So it's a zero of the vector field, okay? Suppose now that the spectrum of the derivative of the vector field in zero has this form. So basically, the Jacobian matrix of the derivative at zero may be written like this. So it contains an op bifurcation and a zero bifurcation, a saddle node bifurcation, okay? This is op-zero singularity. In 1974, Takens described, he has a paper in which he described the normal form of this singularity. So first of all, he changed coordinates and write the normal form of this singularity. What does it mean? It means that the expression, the general expression in cylindrical coordinates of a vector field admitting an op-zero singularity should have this form. And he listed, Takens listed these normal forms in 6 cases. Okay, so there are 6 possible cases for dynamics associated to this normal form. I'm interested in the case 1. In case 1, I'm going to consider A1 greater than 0 and B1 equal to -1. Okay? So Takens, let me point out that these coordinates do not depend on theta. Takens noticed this. Does not depend on theta. So it consider just these 2 components, okay? Just coordinate R and coordinate Z. He consider 2 components and define the generic enfoldings of this op-zero singularity like this. So generic enfoldings as codimension 2. So I need 2 parameters to define generic enfolding of op-zero singularity. And he analyzed this system. He analyzed this system and imposed an open condition. A condition on the coefficients, And under this open condition, he found the following. In fact, it's a result by Gavrilov. So Gavrilov used the result by Takens. There exists a line here in the bifurcation parameter mu1, mu2. Please remind that mu1, mu2 are the parameters that appear here in generic enfolding. There exists a line in which, in this line, the flow associated to this system, generic enfolding, omitting the theta coordinate, has two equilibria. Okay? In addition, I have one connection from P2 to P1 and another connection from P1 to P2. In this side of the line, I have a periodic solution because this connection breaks. In this side, I have nothing. I have no recurrent points. Okay? So, Gavrilov proved the existence of an heteroclinic cycle associated to P1 and P2. Okay? In this side, I have a periodic solution, is attracting. Okay? Here, this heteroclinic cycle is attracting as well because there is an open set here such that all trajectories will approach the heteroclinic cycle. Is attracting by inside, just using this region. There is no open set. Okay? Okay, so, but 2 slides ago, I said that I'm omitting the theta coordinate. When I add the theta coordinate, okay, to the system, I have a heteroclinic cycle associated to 2 equilibria. These 2 equilibria, when I add the extra coordinate, these 2 equilibria are no more saddles, but are saddle foci, okay? And this connection remains, and this connection becomes two-dimensional. So I have what I call a Bykov attractor, okay? So when I add another coordinate, this cycle becomes this cycle, and this cycle is attracting as well, okay? This is just to say what I the remarks that I said. So when I add the angular coordinate, I define a vector field with symmetry and the flow as an attracting heteroclinic cycle associated to 2 saddle foci. The cycle is made by 1 dimension connection and 2 the heteroclinic connection. Okay, basically this is the idea. So let's summing up. I started with the op0 singularity, and under some conditions on the parameters, I can find in the generic enfolding a cycle like this. Well, but wait a moment. The coincidence of these manifolds, so the coincidence in the sphere is the unstable manifold of P minus and the stable manifold of P plus. Okay? When, in general, the coincidence is not a typical behavior, okay? So the coincidence of invariant manifolds is exceptional, and in general, they are expected to split, okay? These authors, Dumortier, Bagnès, Kokubo, Simon, Baldoma, Ciara, they study the case in which they meet transversely. So, in the line, in the bifurcation diagram, I have this heteroclinic cycle. But in general, the coincidence is not typical, so I need to, we have 2 possibilities. Either they intersect transversely, like this, and when they intersect transversely, is already proved the existence of strange attractors, or they do not intersect, like this. Okay, this image is from Dumortier, Bagnès, Kokubo, and Simon. Or they do not intersect. Okay, and they are attracting. Okay, but there are attracting regions. So this is an open problem. could I find strange attractors with this configuration? Okay, this is the problem. Could I find strange attractor with this configuration? Okay, so this ends the second part of my work. So second part of my work, please take into account the following. I have the op0 singularity. There are any generic unfolding as some parameters for which I can find heteroclinic cycle associated to two saddle foci. In the line, there is coincidence of two-dimensional invariant manifolds. In general, this coincidence is not typical, so they can meet transversely. A small perturbation makes them to meet transversely, or they do not meet. So I'm going to construct a model. Describing these properties in such a way I can prove the existence of strange attractors. So this is part 3. I'm going to enter in part 3. I'm going to construct a model in such a way I'm going to prove the existence or not of strange attractors. Once again, the model should translate the properties that I have for the op0 bifurcation. Otherwise, it has not interest. Okay, so the model is, I'm going to consider, in fact, is a three-dimensional family. Okay, depends on two parameters that belongs to an interval, and another parameter that depends on the angle. So I'm going to pass this slide. Is the following. The properties are the following. Suppose that I have a vector field such that I have two equilibria. These equilibria are saddle foci. Is the first and the second properties. Okay? Two equilibria. The two equilibria are saddle foci. Okay? Assuming one condition, the contracting eigenvalue. In fact, the real part of this eigenvalue is greater than the expanding eigenvalue. It's a technical condition in order to impose that the cycle is asymptotically stable. Okay, so I have two equilibria. I have two connections from O1 to O2, two one-dimensional connections, and one two-dimensional connection from O2 to O1 is this. Okay, there are two trajectories, and these manifolds coincide, and these are two spheres. Okay, basically these properties this image translates the property when these parameters are 0. Okay, this set is asymptotically stable. What does it mean? It means that if I start near the cycle, I will approach the cycle. This is important. Okay, well, but which kind of role play the variables a and lambda? For a and lambda, these manifolds persist. What does it mean? It means that for a and lambda, if a and lambda are greater than 0, this one-dimensional connection persists. And I'm going to impose that for a and lambda greater than 0, the two-dimensional manifolds, this and this, do not intersect. This is to translate the property of the op0 singularity, the unfolding of the op0 singularity. Okay? Right? So the model has 6 properties. The 4th property is to construct the organizing center. The 2 other properties is to say that when these parameters are non-zero, the one-dimensional manifolds coincide and the other do not intersect like this. How to analyze the dynamics near this kind of cycle? Basically, the idea is to construct a sequence of cross-sections. Okay? So I'm going to linearize. In fact, I'm going to use a normal form. I'm going to use a normal form near the equilibria. Okay? So it's possible to construct 2 cross-sections in which from one cross-section trajectories go in the neighborhood of the saddle foci, and in the other section trajectories go out. Okay, so I'm going to consider one cross-section here, here the same. Okay, so inside these neighborhoods, the dynamics is basically dominated by the linearization, linear part of the vector field. And in between the cross sections, I'm going to consider global maps, the transition maps. Since the one-dimensional connections are preserved, I'm considering here a linear map. See, in between these two cross sections, I'm going to consider a map like this. Wait, but what is this map? Suppose that I'm considering here a cross section. Cross section is a section where the flow is transverse. Suppose that this gray line is the stable manifold of one equilibrium, O1, for example. And this is the unstable manifold of O2. Since they do not intersect, because it's an hypothesis that I'm going to consider in my model, this is the model of my transition. So the transition as this form, okay? A is this distance, and lambda models small variations of the unstable manifold in the cross section, okay? Is a model, and this model, in fact, is not random. This model has already been considered by Pierre Gaspard, and there are some evidences of the work by Ibanez in which the transitions, the distance between the manifolds have this shape, okay, have this form. So it's not a random transition, okay? So, and the first return map to this cross section is the composition of this set of maps, okay? So to analyze, to check the dynamics in the first return map, to analyze dynamics near the cycle, I need to analyze dynamics of the first return map. So the first thing to do is to write carefully the first return map, okay? And the first return map depends on these parameters. K omega depends on the imaginary part of the eigenvalues. A depends on this distance, and lambda is the variation of the unstable manifold in the cross section. So this is a model, okay? It's a model. In fact, this should be phi of x, because it's not a sino, it's phi of x, okay? So this is the first return map. Our first result says the following. Suppose that this ratio is less than a given number that depends on the imaginary part of the complex eigenvalues of the saddle fossil. Okay? So if this inequality holds, the first return map has an invariant curve that is a maximal attractor for the first return map. Wait a moment. If I can find an invariant closed curve that is attracting for the first return map, what kind of dynamics should I have in the flow? I should have a torus, an invariant torus that is attracting. Okay? So if this happens, I have an invariant curve. Okay? So the idea that you should have in mind is the following. So suppose that I have a cross section. So there is a line here in such a way that the flow the trajectories will approach this curve. To prove this theorem, I'm going to use the Afremovich-Hanow's principle. It's to check properties. It's basically to check all properties. And when there is a property that does not hold without this hypothesis, so this is why I add this hypothesis. Okay, so if this happens, I have an invariant torus. So if I make a bifurcation diagram, this means the following. This property is translated in this graph. If G is the graph of this map, where this is the variable, okay, this means that below this curve, I have an invariant torus. So the flow has an invariant torus because the first return map has an invariant curve that is attracting. Okay? Second result. So this is a picture. Second result. Suppose now that the ratio is greater than the number that depends on the imaginary part of the complex eigenvalues. If this happens, I have a horseshoe. It's basically the same idea that I presented in the first part of my talk. I have a horseshoe. This means that the flow is topological conjugate to a Bernoulli shift on two symbols. Okay? So if I draw the graph of this map, where this is x, this is, if I draw the map, the graph of this map, this means that above the graph of f, it corresponds to parameters where I can find horseshoes, okay? Where I can find horseshoes. So this is, the next slide is the image of the horseshoe. I'm going to omit details, but this is the image of the horseshoe. It's not a single horseshoe, in fact, I have an horseshoe with infinitely many legs, but infinitely no, but finitely many, with a large number of legs, okay? This is just a picture. Okay, so in the middle, so above the graph of f corresponds to parameters where I can find chaos, horseshoes. Below the graph of g, I can find an invariant torus. So what happens in between these two graphs? So suppose that I fix k omega, and what happens in between? In between, I can find here is invariant torus, is this. Here is a horseshoe, is this idea, okay? In between, when I am traveling inside this line will be transformed like this. So is what Afremovich called is the torus bifurcation or torus breakdown, okay? Is the torus breakdown. And at this moment, I can use results by Arnold, Haronson, and Boyland, saying that in between, when I break the torus, in this bifurcation diagram, I can find a line in which I can find homoclinic tangencies, but wait. When lambda is equal to 0, I have a torus. Okay. In between these two lines is a saddle mode bifurcation emerges. So I have, in the middle, I have a saddle and a sink. This is image for the first return map. When I increase lambda, when I increase this ratio, in fact, I can find here a line in which the torus is broken, and I can find associated to the saddle that are born inside this wedge, I can find homoclinic tangency. This saddle is dissipative. This is a property that is easy to check that is dissipative. And I have homoclinic tangency. Wait, since you have homoclinic tangency, you have a strange attractor because this is my part 2. This is the part 2 of my my work. So in between, I find a line in which I can find homoclinic tangencies, and then nearby strange attractors by the result by Moore and Diana. Okay, so using Arnold tongs, there exists a positive Lebesgue measure of parameters where I can find a strange attractor. Okay, so this model, so to finish this part, this model, the model that I construct, translate the properties of a generic enfolding of op0 singularity. Okay, so this means that perhaps when the manifolds in the op0 singularity do not meet, I can have strange attractors. Well, but you can say, but this is a 3-parameter family. Could you improve the result? And in fact, so this is this slide is what I said, that this here in this region, okay, when I have a periodic solution, I can find strange attractors. So, but this is a 3-parameter family. Could you improve a little bit the result? And yes, it's possible to improve the result. It's possible to, instead of considering a 2-parameter family here, A and lambda, I'm going to consider just a 1-parameter family like this, lambda h of x, where h of x is greater than 0. And when this holds, in fact, this is a preprint, and in fact, I think that we have a strange attractor, and we have a set of Lebesgue measure in the space of parameters where I can find strange attractors. So, strange attractors means that the cause is observable, and moreover, the set of parameters that exhibit strange attractors has positive Lebesgue measure. Okay? Do you understand that there are two things here? Because chaos is observable, it means that there exists an open set of trajectories that converge to this strange attractor. But in the space of parameters, this can happen with 0 Lebesgue measure. So I'm in this result. With this result, we have that is observable. We have the two things: is observable and is persistent. Okay. If you move a little bit the parameter, it's probable that strange attractors still exist. Okay? Okay, so now let's give an example. This example is a system with symmetry in which I can illustrate what I said in the theory. So this is a dynamical system with 3 parameters. So it's a differential equation dimension 4 with 3 parameters. The parameter tau1, parameter tau2, and parameter omega. Okay? Tau1 and tau2 play the same role as A and lambda in the previous section. When both are equal to 0, so I'm going to go back. Please remind that when both parameters are 0, I have a cycle. Okay? And tau1 and tau2 will play the role of these parameters. So this is the same. Where tau1 and tau2 are equal to 0, I have a heteroclinic cycle. Okay, this is the picture. So I have the one-dimensional connection, and this illustrates the two-dimensional connection. Okay, here the same one-dimensional connection, and this represents the two-dimensional connection. This is the first return map. When one is greater than 0 and the other is equal to 0, I have a torus. Okay, I have a torus. Okay, the two equilibria and the torus here, and the first return map. Of course, when I cut a torus, I should have an invariant curve. Okay, when both are greater than 0, this suggests the existence of strange attractors. And I brought here the Arnold tongues, and you may see here that this is the theoretical part. So there exists here a line where I can find tangencies and then strange attractors. Numerically, when I draw the Lyapunov exponents, I see 2 regions leaving the Arnold tongue where I can find strange attractors. Okay? In another tongue, 2 regions, they correspond to these lines. So this is nice that these numerical simulations are very recent, and this picture is from the 80s. So it's nice to have a numerical simulation that confirms the existence of strange attractors. Okay, suggest the existence of strange attractors. Okay, conclusions. Wait, we are finishing. I'm finishing my talk. Conclusions. The route to create strange attractors. So, what is the route? I started with a singularity. I analyzed generic enfoldings. There are several papers where these generic enfoldings have been already studied. For example, Ibáñez has a list for generic enfoldings in the nilpotent singularity of dimension 3 and dimension 4. Then, in these generic enfoldings, they are vector fields. And sometimes these vector fields have symmetries. So let's find heteroclinic cycles and networks. And when you break the heteroclinic cycle and network, generically, there are tangencies. Since there are tangencies, I can find strange attractors. But why this route? This route is because, in general, singularities are easy to detect. To detect the singularities, just to check the existence of singularities, just to find the eigenvalues. So, in general, singularities are easy to detect. Okay? Ongoing work. So, at the moment, I'm going to describe with more precision what is happening in the Arnold tongue. Arnold tongue is the resonance wedge. Sometimes it's called the resonance wedge. Sorry. And I'm going to relate the dynamics of the first return map with the study by Wang and Lisa Young. Okay, and another open problem is to find strange attractors with two Lyapunov exponents, because in general these strange attractors have just one Lyapunov positive. Here is positive. It's just one positive Lyapunov exponent, and analytically we don't know any examples coming from singularities with two positive Lyapunov exponents. And I'm finishing my talk. Okay, so if you have questions, please let me know. Okay.
Thank you very much, Alexandre. We could hear you. You are a specialist on Bykov attractors. It was a very nice talk. Thank you.
Okay, thank you.
Let's see if there are questions for you in the chat. We can wait some moments before they eventually come. I have one question.
Okay.
I have two questions, but first it's a basic one. When you have this structure in Bykov attractors, so you have this one-dimensional and two-dimensional invariant manifolds. So are you necessarily looking inside a three-dimensional compact manifold?
Yes.
Is the setup? I mean.
Yes. In fact, it's possible. So in the setting, I heard an echo. In the setting, I'm working in compact three-dimensional manifolds. But there are works in other unfoldings where I can restrict to the center manifold that is three-dimensional. So perhaps if you have, for example, singularity, nilpotent singularity of dimension 5, it's possible under some conditions to reduce to a center manifold of a three-dimensional center manifold. So perhaps it's possible. Okay.
Okay.
To extend the results to four-dimensional manifold. And I have an example in which, for example, in the nilpotent singularity of dimension 4, generic enfoldings as a homoclinic cycle to a bifocus. The bifocus, you should work in dimension 4. So, okay.
Right. Okay. And it wasn't. I couldn't see. I'd like to feel the symmetries in the end of your part. It wasn't clear for me when you mentioned that you would have symmetries in that map, but I couldn't. So yes. What is the symmetry actually there?
Okay. In fact, when you have when the two-dimensional manifolds, when they coincide, in general, this corresponds to a SO2 symmetry. I'm going to my slides.
Okay.
I'm going to my slides, and in my slides, in fact, when you omitting this term, when Takens omitted these terms, this means that when you add this term at the end, the differential equation has SO2 symmetry.
Okay, so when you put theta in the play,
yes.
So
yes.
then you have the SO2. Okay.
The SO2 symmetry. Okay, so it's when you add the angular coordinates, you define SO2 equivariant symmetry. And is this continuous symmetry, is this SO2 symmetry that forces the existence of a two-dimensional connection, that forces the existence of the sphere. Is this SO2 symmetry that forces the existence of the sphere. Okay, and the example that I present in part 5 of my work, they have the example as SO2 symmetry as well. Okay, I omitted this part, but the example as SO2 symmetry.
Okay, right.
Okay, I forgot to say that why I call Bykov Attractor. Bykov Attractor is a tribute to Bykov. Bykov is a Russian mathematician and is a tribute to Bykov that studied the same similar cycles. He studied cycles in which the two-dimensional manifolds meet transversely, but this kind of tribute to him. Okay.
Very nice.
Okay.
We have some questions. So Reinaldo Rosalf is asking you, I just read it. I understand correctly, your theorem from 2020 also applies to systems with multi-stability. That is, those that have more than one strange attractors in the phase space. An example is the Kuramoto-Szywaczyński equation.
Yes. In the Kuramoto-Szywaczyński equations, there are parameters for which I can find a strange attractor. But in this Kuramoto-Szywaczyński, the manifolds meet transversely. So it falls in the work by Ibáñez. So the manifolds meet transversely. Okay. It's not my case. Okay. But the organizing center is a Bykov cycle. Yes. Yes.
Right. Thank you.
If you send your email, Reinaldo, if you send your email, I can explain with more details this. But it's a work by Santiago Ibáñez and José Ángel Rodrigues.
That's very good.
Okay.
So, once again, thank you very much, Alexandre. Thank you.
It was a pleasure. That was at the beginning, but it was a pleasure. Okay, thank you, Miriam.
Many, many thanks. So. So we are reaching the end of this first part of our talks of the second day of the workshop. So just reminding you that we will be showing some other videos at 2 p.m. Okay, so hope I'll see you there. Good afternoon, good night. Thank you very much.
Okay. Good morning and welcome again, everybody, to this morning session. Okay, now it's no music. It's my pleasure to introduce the third speaker of this session. And welcome again, everybody, to this morning session. And the third speaker is Bruna Oréfice Okamoto from São Carlos. And she belongs to the branch of the Singularity group, which is not in the University of São Paulo, but in the Federal University of São Carlos. And she's going to speak about isolated determinantal singularities and function germs over them. Okay, Bruna. And she belongs to the branch of the...
Hello, thank you, Juan, for the presentation. Good morning, good afternoon, good night, depending on where you are.
To speak about isolated determinantal singularities.
I'll just present my screen. I'm listening. Okay, now I'm not anymore. Well, I'd like to say thank you to the organizing committee of the workshop for organizing this workshop and also for the invitation. It's always a pleasure for me to be here and have this opportunity to present my work. Well, as Juan said, I will talk about isolated determinantal singularities. The idea here is to show a little bit of every work I collaborate about this issue. The works were done in partnership with Daiane Alicia Henriquemente from Universidade Federal de Lavras, Rafaela Soares de Carvalho, my ex-PhD student from Universidade Federal de São Carlos, and with my advisors, Juan Roseno Ballesteros from Universidade de València, and João Nivaldo Tomazella, also from UFSCar. I divided my lecture in two parts. In the first one, we will see the invariants we defined for an isolated determinantal singularity. And in the second one, we will see how those invariants are related to the singularities of these families. And this is why I have two introductions. So the first one, we know that the Milnor number and the polar multiplicities are important invariants of an isolated complete intersection singularity, which we are used to denote by ICES. And a natural generalization of complete intersections are the determinantal singularities. Determinantal singularities are those which are defined by the minors of a matrix with the expected codimension. So, in the first part of this talk, we will see the definition of a determinantal singularity and some invariants of them. Well, many authors are working with determinantal singularities. I will cite here Chachapoya Siskin, Damon, Ebelin, Frobes-Kruger, Gaffney, Guzenzade, Pereira, Pike, Rua, Zach, and I'm so sorry if I forget someone. Well, we remember that a complete intersection is a germ defined as the zero set of an analytic map, let's say psi, from Cn to Cp. And in order to be a complete intersection, my germ has to have the same codimension of the zero in Cp. The codimension of the variety I'm pulling back then. And the determinantal singularities are defined in the same way. I have to define one thing first. I will consider three integer numbers, S, M, and N, like this, with this property. And I will denote by capital N, M, N, the set of the complex matrices with size M by N, M rows and N columns. And I will denote by M, M, and S, the subset of the matrices matrices with rank less than S. We know that this subset is an algebraic variety of MMN, and that the codimension of this algebraic variety is equal to M minus S plus 1 times N minus S plus 1. This is the variety I want to put in the place of the zero when I define the IDS in the place of ICES. Well, I will consider a holomorphic map germ psi from Cn to MMN, and I will call X the germ defined as the inverse image of the matrices with rank less than S by psi. I can say it in another way. If I look to this psi as a matrices whose elements are holomorphic function germs from Cn to C, then I have a M by N matrices, and I can look to the ideal generated by the minors of size S of this matrix. My X is then the zero set of this ideal. Well, I will say that my X is a determinantal singularity of time type M and S if it has the expected codimension. I mean the codimension of M and S, which is M minus S plus 1 times N minus S plus 1. If besides I have that S is equal to 1, or N is smaller than M minus S plus 2 times N minus S plus 2, and that my X is smooth at small x in X for X not equal to 0 in a small neighborhood of the origin, then I'll say that my germ X is an isolated determinantal singularity, and I will abbreviate it by an IDS. Here, S equal to 1, when S is equal to 1, I have just an ICES. And this is a technical condition I had to put in order to make the proofs. Well, now we want to define what would be a Milnor number for an IDS. We remember that the Milnor number was defined already for ICES, and it is equal to the number of spheres in the bouquet given by the minor fiber of my ICES. I will proceed in the same way with the IDS. So, for each matrix A, each complex matrix A of size Mn, I will denote by psi A the map from Cn to Mmn, who takes an X to psi of X plus A. Just remember that psi of X is the germ which was defining my IDS capital X. And I will denote by XA the inverse image by this map of the set of matrices with rank less than S. Well, in 2013, we showed that there exists a non-empty zero-risk open subset W in the set of all matrices, such that the XA is smooth, and the Euler characteristic of XA, which denote like this, does not depend on A in this W. Well, this XA here can be seen as the Milnor fiber of my IDS. Therefore, we defined the vanishing Euler characteristic of the IDS X as -1 to the dimension of X times the Euler characteristic of XA -1. And I will denote this as nu of XA. Well, here I have some remarks. If my XA was a bouquet of spheres, this number would be the number of spheres in this bouquet. And then this would be the Milnor number as it was defined for analysis. But this is not the case always for IDS. This fiber may not be a bouquet of spheres. And this is why I called it the vanishing Euler characteristic instead of the Milnor number. Well, after we define kind of a Milnor number, the vanishing Euler characteristic of an IDS, we have a lot of work now because everything that we know for the Milnor number of an IDS, we can ask if it's true also for the Milnor number for the vanishing Euler characteristic of an IDS. And I have some things done already. If the dimension of my IDS is equal to 0, then the vanishing Euler characteristic of it is equal to the dimension of the local ring of X as a C-vector space minus 1, as it was new for analysis. Moreover, if the dimension of my IDS is equal to 2 to 1, I mean my IDS is a curve, then its vanishing Euler characteristic is equal to the Milnor number of the curve, as defined by Bushwitz and Groyer in 1980. If the dimension of my IDS is equal to 2, then its vanishing Euler characteristic is equal to the medium beta number of my fiber, and then it can be called the Milnor number as for analysis. The vanishing Euler characteristic was defined in the same time and independently for other authors too. I mean Pereira and Ruas and Damon and Pike. Everything's right?
Yes, Bruna, everything is okay.
Thank
And
you.
continue. Welcome.
Well, another important invariant of an variety is the polar multiplicities. For a variety with dimension G, the MI polar multiplicity is always defined for I from 0 to D minus 1. The D polar multiplicity of some kind of varieties were already defined when I started to study. And they are important, for instance, because if I consider a family of ices, then it is Whitney singular, if and only if all the polar multiplicities are constant in the family. And now I want to define then the polar multiplicity of an IDS. For the aces case, the polar multiplicity is equal to the Milnor number of a generic linear projection defined on the ices. And it will be the same here for an IDS. But I have to work to show that this is well defined. Then, during my PhD, we showed this theorem. Let P from Cn to C be a generic linear function, and a generic matrix. Then we showed that the number of critical points of P restricted to Xa is equal to the vanishing Euler characteristic of my IDS X plus the vanishing Euler characteristic of my IDS here in P minus 1 of 0, X intersection with P minus 1 of 0. And also, we showed that if the dimension of X is equal to D, then the local Euler obstruction of my X is equal to minus 1 to D minus 1 times the vanishing Euler characteristic of X intersection to P minus 1 of 0 plus 1. Well, I'd like to define this number here to be the polar multiplicity of my IDS, the diff polar multiplicity of my IDS. Here in the first part, I showed that this number only depends on X and on P. And on the second part, if I just isolate here my nu of X intersection to P minus 1 of 0, I can substitute it there. and I have that this number does not depend on anything else than x. And I can define the dipolar multiplicity of x is equal to the number of critical points of P restricted to XA, where P is a generic linear map and A is a generic matrix. And this D, which appears here, is the dimension of my IDS. Well, as for the IC's case, I can show that the vanishing Euler characteristic of an IDS can be written in terms of the polar multiplicities. For this, if my IDS has dimension D, then I will show that XA has the homotopy type of CW complex with any E of X cells of dimension E, for E from 0 to D. And with this, I can show the 0 here does not exist. That's that the vanishing Euler characteristic of X is equal to -1 to D times the sum of -1 to Y mi of X minus 1, as for the ICs. Well, those are the invariants that we defined for an IDS. We now want to consider function germs over my IDS. So I will consider a function germ f from x to c, holomorphic with isolated singularity, where x is an IDS. And I want to define a Milnor number for it. Well, I remember that the Milnor number of a germ with isolated singularity over Cn is equal to the number of Morse singularities which appear in a morphification of my f. So I will do the same here again. For each vector A in Cn, if A is equal to A1 until An, I will denote by Fa the function which takes x1, xn to f of x plus a1, x1 plus a2, x2 until an, xn. And we showed in 2013 that there exists an unempty open subset W in Cn times mmn, so that for all small a and capital A in W, we have that xa is smooth, Fa restricted to xa is a Morse function. And moreover, we showed that the number of critical points of A restricted to xa does not depend on AA in W. Because of this, we can define the Milnor number of F by the number of critical points of FA restricted to XA with AA generic in my W. And also, we define the vanishing Euler characteristic of my fiber, F minus 1 of 0. Remark that, different of the case where I was considering a projection here, this variety is not a determinantal singularity. It's kind of a determinantal singularity in F minus 1 of 0. It's not the same. So I really need to define this. And I defined the vanishing Euler characteristic of this fiber as -1 to the dimension of x minus 1 times the Euler characteristic of XA intersection 2 FB minus 1 of E minus 1 with B, A, and E in Cn, M, N, and C generic. Well, if X were an ICES, the Milnor number of the function as we define would be equal to the dimension of the C space given by the quotient of the ON, the ring of holomorphic function germs from Cn to C, over the ideal which defines the singular set of F which would be the equations of psi plus the Jacobian, the maximum minors of the Jacobian matrix of the equations of x plus f. And therefore, by the Solfermus-Legros formula, we would have that the Müller number of f would be equal to the Müller number of x plus the Müller number of the fiber. If I'm not working with an ICs anymore, but with an IDS, then the Müller number of f, the function that I just defined, cannot be calculated as that dimension of C-vector space anymore. But the Legros formula still works. I have that the Müller number of f is equal to the vanishing area characteristic of x plus the vanishing area characteristic of x intersection 2 f minus 1 of 0. And also, in 2016, we were able to find the relation between these invariants and the local Euler reconstruction of the function in this way. If my IDS has dimension d, then we showed that the local Euler obstruction of f, as defined by Brasileiro, Massa, and Paramesoran in 2004, is equal to minus 1 to d times the vanishing Euler characteristic of my fiber, x intersection 2f minus 1 of 0, minus the vanishing Euler characteristic of x intersection 2p minus 1 of 0 for p, a generic linear projection. Well, I can just use the Legros formula here. This thing is equal to the Müller number of f minus the vanishing Euler characteristic of x. And this one, the Müller number of p minus the vanishing Euler characteristic of x. I just cancel the vanishing Euler characteristic of x, and I would have that the local Euler obstruction of the function is equal to minus 1 to d times the Müller number of f minus the Müller number of p. But since p is a generic linear projection, the Müller number of p is equal to the dipolar multiplicity of x. And I have this relationship here. Okay? Juanjo, everything's all right?
Hello, Bruna. Everything's all right. There is a question by Meral Tosun. Maybe you can answer now. So she's asking if X is an embedded or in which space? X is embedded in which space?
X is in Cn.
Cn, okay.
C2 capital N. This was the question?
I think so.
Okay. Well, so this was the first part of our work where we defined the invariants and relate them with what we knew before for ICs. Now, we use these invariants to study the singularity of families of determinantal singularities and also of functions over determinantal singularities. So I bring here another introduction. So about this, in 1976, Lei and Ramanujan proved that a one-parameter family of isolated hypersurface singularities, which I denote here by xt, of dimension not equal to 2, has constant topological type if the Müller number, which is denoted by mi of xt, is constant on T. Then, in 1991, Paramesoran showed that the same result is true for a family of ICs of dimension still not equal to 2. In 1980, Bushwaits and Groel studied the results for space curves. The topological triviality of the family was obtained by using an appropriate version of the Müller number. In 1971, Zariski showed that for plane curves, the mi-constant condition is also equivalent to Whitney singularity. And in 1975, it appears the the Briançon-Speder example, which show that this is not true anymore for hypersurfaces with dimension higher than or equal to 2. In 1973, Tessier showed that for a family of hypersurfaces, the family is Whitney singular, if and only if the M* sequence is constant on the family. And in 1996, Gaffney showed that a family of ices of any dimension d is Whitney singular, if and only if the polar multiplicities mi of xt for I from 0 to d are constant. About function germs over singular varieties, Nuno Ballesteros and Tomasella in 2008, they work with families of function ft from xt to c, where xt are curves. And they showed that if f is constant, then the family is good, that f is topologically trivial and good, if and only if it's constant, and that f is Whitney singular, if and only if it is constant, and the zero polar multiplicity of xt is constant. Well, what I want to do now is to do things like this for families of IDSs or functions over IDS. So just to remember, I have X, an IDS, defined by a map germ psi from Cn to mmn. I mean, the germ X is given by the inverse image by the psi of the matrices with rank less than S. And I will consider which we call the determinantal deformation of my IDS. A capital psi, like this, from C times Cn to mmn, so that psi of 0x, x, is equal to the small psi of x for all x. And we denote psi t of x, capital psi of tx, xt, the determinantal variety defined by psi t, I mean the inverse image of the matrices with rank less than S by psi t, and by curl x, the capital psi minus 1 of the matrices with rank less than S. So for a family like that, we'll say that it is no constant if the vanishing Euler characteristic of each x time, xt, is equal to the vanishing Euler characteristic of x for t small enough, that it is a good family. It has isolated singularity uniformly. I mean, I can choose a representative for all of them with just one singularity. And topologically trivial if there is a homeomorphism H from x to c times x, which commutes with the projection. And also, I'll say that this family is Whitney singular if it is a good family, and if t is the x c times 0, then x minus t and t satisfies the Whitney conditions. Well, about this, in 2018, we showed that if x is a d-dimensional IDS and xt is n determinantal deformation, then the vanishing Euler characteristic of x minus the sum of the vanishing Euler characteristic of xt in x for all x in the singular set of xt is equal to minus 1 to d times the Euler characteristic of xt minus 1. And as a corollary, I get that if xt is a topologically trivial deformation, then this is equal to 0, and therefore the vanishing Euler characteristic of x is equal to the sum of the vanishing Euler characteristic of xt in nx in the singular set of xt. And also, for the case of two-dimensional IDSs, we can conclude the upper semi-continuity of the vanishing Euler characteristic. That is, only if the dimension of x is equal to 2, then the vanishing Euler characteristic of xtx is less than or equal to the vanishing Euler characteristic of x for any determinantal deformation xt and for any x in the singular set of xt. And about the Whitney singularity, we got this result. A good family of d-dimensional IDSs, which I put xt here, is Whitney singular if and only if all the polar multiplicities are constant on T. This is the same result that it was obtained for ICEs by Gaffney. Okay. Well, more recently, you are interested in studying the singularities of families of functions over IDS. So, I take a function germ with isolated singularity, f from my IDS x to c. And we consider a curly X family like we defined before, and an unfolding of f in this way, which a capital F, which takes tx to something like t and ft of x, and I assume that this capital F is origin preserving. I mean, 0 belongs to xt, and ft of 0 is equal to 0 for it is small enough. Then I have a one-parameter family of function germs here from ft from xt to c. And again, for this family, we say that it is mi-constant, of course, if the Milnor number of each ft is equal to the Milnor number of f for it is small enough. Like before, we say that it is good if it has an isolated singularity uniformly. You say that it is topologically trivial if there are homeomorphism map germs G here and H here, which are unfolding of the respective identities, such that when I consider U here, the trivial unfolding of F, this diagram is commutative. And I say that the family is Whitney singular if it is good, and it admits a regular stratification given in this way. A stratification of the source, which I call A, which is equal to curl x minus f minus 1 of t, f minus 1 of t minus s and s, where s is d times 0 in c times cn, and t is d times 0 in c times c. And stratification in the source, A prime, which is c times c minus t and t. Now, our goal here is to study when family is Whitney singular. And about this, in 2020, we proved kind of the principle of the conservation of the number for families of function germs on IDS. That is, for t small enough, the Milnor number of f is the sum of the Milnor number of ft at z, where z belongs to the singular set of ft. I just remark here that the singular set of ft is the points where xt is singular, or xt is not singular, but ft at this point is not a submersion. And get some easy corollaries of this theorem. The first one, if you assume that curl X is a good family, then f is mi-constant if and only if it is good. Okay, I have this equality here in order to be me constant, this has to be equal to me of ft0. And also we show the upper semi-continuity. In this case, I mean, for all x in the singular set of ft, and for t is not enough, the Milnor number of ft at x is less than or equal to the Milnor number of f. And another corollary, if the curl X, the family of IDS is good and topologically trivial, then we showed that the vanishing order characteristic of the fiber f minus 1 of 0 is equal to the sum of the vanishing order characteristic of xt at y, where y belongs to the singular set of ft in xt0, the smooth part of xt, plus the sum of the vanishing order characteristic of this fiber here, xt intersection 2 ft minus 1 of 0 y, where y belongs to the singular set of ft. For this result, I brought a sketch of the proof. So let's go. Since my family curl X is good, I can choose a representative in D times U, where D and U are open neighborhoods of the origin C and Cn respectively, such that the singular set of xt is just 0 on U for all T and D. And we will work over this representative. We consider F in this representative. Well, by the theorem we just showed, we have that the Milnor number of F is equal to this sum here. Now, here I would have to put the sum over the singular set of xt of Milnor number of fty. But since I'm in this representative, I don't have to put this. Now I have just 0. So this from the theorem. And from the Legros formulas, I have this one. This Milnor number of f is equal to the vanishing Orley characteristic of x plus the vanishing Orley characteristic of x intersection 2f minus 1 of 0. I just copy here in the other slide. Then, now I will apply the Legros formula again on me of ft. If I apply the Legros formula here, I have that me of ft is the vanishing Orley characteristic of xt plus the vanishing Orley characteristic of xt intersection 2 ft minus 1 of 0. And I have this thing here, and I just skip this part that I do not use anymore. The vanishing Orley characteristic of x plus the vanishing Orley characteristic of x intersection f minus 1 of 0 is equal to this sum here. Well, now I use the Legros formula. Oh, no, sorry. I have to make a remark before. Since x good is topologically and topologically trivial, from our result from 2008, I had that the vanishing Orley characteristic of xt is equal to the vanishing Orley characteristic of x. Therefore, I just cancel here these things and get this relation to the vanishing Orley characteristic of the fiber. I will copy it again. It's here. Now I will use the Legros formula again, but now for each of these Milnor numbers here. Then each one of them can be replaced by the vanishing Orley characteristic of xty plus the vanishing Orley characteristic of xt intersection 2 ft minus 1 of 0y. And now, in order to conclude the theorem, I just take this part here and put together with this one. And I get what I want. Well, remember, we were interested in the singularity of this family. And I can show that if f is with me singular, then it is me constant, and the polar multiplicity of the family of the IDS is constant. I mean, f is me constant, and then I of xt for I from 0 to d are constant on t. But we want some kind of reciprocal. What I have to put that, what I have to assume to say that my family is Whitney X singular. And for this, if I'm working with families over ices, I have my result already from 0. If you are working with a family of ices, I mean, if S is equal to 1, if I have that F is me constant, the polar multiplicity of xt are constant for if I from 0 to d, and the polar multiplicities mk of the fibers xt intersection 2 ft minus 1 of 0 are constant for k from 0 to d minus 1, then my family F is Whitney X singular. Remark here, if xt were an isis, in this case, this variety which appeared here is also an isis, and this polar multiplicity here was defined by Gaffney. So my problem now to go to general cases of IDS is that this may not be an IDS again, and I have to define this invariant. I have to define the polar multiplicity md minus 1. D minus 1 is the dimension of this variety here. Now I have to define this polar multiplicity. And we will do this in the natural way. It will be the number of singular points of a generic linear projection over a deformation of my IDS. But I will have to work again to show that it's well defined. From now on, I will denote by I my fiber, because I don't want to write it every way. Well, we were able to show that let P a generic linear function for a vector alpha from in Cn times mmn times C generic if alpha is equal to BIE and Y alpha is equal to XA intersection 2 FB minus 1 of E, then the number of critical points of the projection over epsilon alpha is equal to the vanishing order characteristic of Y, my fiber, plus the vanishing order characteristic of Y intersection 2 P minus 1 of 0. This number here is what I want to call my polar multiplicity, my D minus 1 polar multiplicity. And now I show that it depends on Y, I mean on X and F, and on P. I have to take this P off here. And the process is the same. So by Ley and Tessier from 1981, I know that the Euler characteristic, the Euler obstruction of Y is equal to the Euler characteristic of Y intersection 2 P minus 1 of T. And we showed that this is equal to minus 1 to D minus 2, the vanishing Euler characteristic of Y intersection 2 P minus 1 of 0, 0 plus 1. Well, then I just isolate this thing here, substituting the slides before, and I have that the number of critical points of P restricted to Y alpha is equal to the vanishing Euler characteristic of Y plus minus 1 to D minus 2, the Euler obstruction of Y plus minus 1 to D minus 1. And what is important is that it only depends on Y. And I can define the D minus 1 polar multiplicity of Y is equal to this number, the number of singular points of P restricted to Y alpha, where P is a generic linear function, and alpha is a generic vector in Cn times mmn times C. Well, now I have my d-1 polar multiplicity of my fiber, y, which was x intersection to f-1 of 0. And I have to work with its invariance as it was done for ices or for the Milnor number of an IDS. And the first thing we showed is that the vanishing Euler characteristic of the fiber can be written in terms of its polar multiplicities. It's equal to -1 to d-1, this alternative sum of the polar multiplicities until d-2 -1 plus the d-1 polar multiplicity of y. Well, and we already had showed that the vanishing Euler characteristic of x was written in terms of the polar multiplicities. Now we showed that the vanishing Euler characteristic of y, which is the fiber of f, is also written in terms of the polar multiplicities. Then I should have put here, but I didn't. But then the Milnor number of f can be written by the Legouel formula in terms of the multiplicity of x and the multiplicities of y. And because of this, I have this corollary. If f is the family of functions, like I defined before, with isolated singularities on IDSs, if I have that the polar multiplicities of xt and the polar multiplicity of yt, here by yt, I mean xt intersection to ft-1 of 0. If these numbers are constant, then f is a constant family. And about the Whitney singularity, if y is this fiber here, if it is a good family, and then the polar multiplicities of yt are constant on t, if and only if this pair here satisfies the Whitney conditions. And finally, what we're looking for since the beginning, the family F is Whitney singular, if and only if my family of IDS square X is a good family, the polar multiplicity of xt and the polar multiplicity of yt, of the family of IDS and of the fibers, are constant on T. This was what we're looking for. I brought here some reference that I cited in the talk. And the first one is where we relate the invariance of the IDS with its Euler obstruction. Here, this one with Rafaela Soares de Carvalho, Nuno Ballesteros, and Tomazello is the last one, where I studied singularity of families of functions over IDS. This one is the paper from my thesis, where we defined the invariance of isolated determinantal singularity. And this one is the paper where I studied the X-singularity of families of isolated determinantal singularity. Now, this is it. Thank you guys very much for your attention.
Okay, thank you very much, Bruna, for your nice talk. So let's see if there are any questions or comments. So I can make a question to have some time. So you mentioned the Le-Ramanujan result for families of hypersurface singularities with hypersurface isolated singularities, and also for ICEs. So can you say something for determinantal varieties or for functions on determinantal varieties about topological triviality?
Okay, thank you, Juan. Yes, I can say about determinantal varieties, it is in the same paper from where we study the Whitney singularity of determinantal varieties. There, I have the result like that. Is still 4 dimension, not equal to 2. and I have to put some more hypotheses. I mean that I have to assume that the fiber, and it has kind of a bouquet of spheres structure. Then I didn't put it here because I thought that was there was no time.
Okay, and for functions, it's more difficult, no?
It's more
topological triviality of functions is much more difficult.
Yes, this way didn't work still.
Okay. There is a question by Roberto Jiménez Conejero. So, in a family of IDS, why do you need the good condition if you already ask for x minus t to be a stratum? In order to it to be an stratum, I need the good conditional, because if I don't assume that the family is good, then I could have I could have singularities out of x minus t. Mm-hmm. Yeah, I think so. So
yes,
the condition, the good condition is just to have x minus t as a stratum, no?
Yes.
Yeah. Okay. Any other question? One question by David Trauman. So I think Teissier showed mu star constant implies Whitney for a family of hypersurface in 1973. The converse is actually due to Briançon-Spider in Fourier 1976.
Oh, I'm so sorry.
Okay. Okay. Any other question or comment? There is a question by Sidiña. It's a question related to Roberto Jiménez talk. So at least in the case d equal 2 for surfaces which are IDS, do you expect that the mu constant is sufficient for good condition?
I don't know. I don't know, Sidiña. I'm sorry.
Yeah, difficult question.
Yes.
So one more by Terry Gaffney. Do you have formulas for the vanishing Euler characteristics?
Formulas for the vanishing Euler characteristics. Yes, I can compute it in terms of the multiplicities. I don't know if I've put it here. Thank you, Terry, for the question. You mean something that I can put at singular? I can do it by using the Turing transformer of it. The other polar multiplicities I can calculate in singular, and the medium polar multiplicity I have to go to the Turing transform. Was this the question?
Okay, there is anything else? So I think it's okay. So let's thank Bruna again for the nice talk. Okay.
Thank you.
Okay, so I have not the program in my front, but we will continue later. Okay. Thank you very much, everybody.
So, hello, everybody. I just would like to remind you that today at 2 p.m., we will have another parallel section. And it is a pleasure to me to introduce those talks. So the first one will be Guilherme Peñafort Sanchez, that will talk about K-folding maps and the robust features of surfaces in R3. The next will be Roberto Jimenez Conejero, that will talk about monodromy of germs of analytic functions without fixed points. After the speaker is Graham Heath, that will talk about contact of surfaces with circles and Euclidean invariants. Then we have a break, and after we return with Sansek Ishiki, that will talk about refinement of transversality theories. And after Yanlin Li, that will talk about tangent development, tangent develop, please, sorry, and thereby developments of framed curves. And after, and here you can find the poster section of today. Okay, thank you, everyone.